So, in this video we will solve some exact equations. So, let us solve some exact equations now, and also we will see how to reduce non-exact equations into an exact equations, and then we can integrate directly because we know the technique of how to integrate an exact equation. Okay. So, this is called the method of integrating factors. So, you look for a certain integrating factor. So, when it is non-exact equation, you look for some function, you multiply it to the equation, then it becomes an exact. So, such a function which you multiply to the equation is called an integrating factor. We will see how to find these integrating factors. Okay. I'll give an example of exact equation that can be solved with the procedure I explained you earlier. So, example. Five x power 4 plus 3x square y square minus 2x y cube dx plus 2x cube y minus 3x square y square minus 5y power 4 into dy equal to 0. So, how do we solve this differential equation in the form which is in the form m dx plus n dy. So, this is in the form m of xy dx plus n of xy into dy equal to 0. So, in the procedure we just have to check whether the given equation is exact or not. The condition for exactness is dou m by dou x dou y, dou m by dou y is equal to dou n by dou x. We will check this condition. If this condition is satisfied, we know how to write the solution of this equation directly. Okay. So, what is dou m by dou y is 6x square y second term minus 6xy square, that gives the third term. First term is only function of x. So, the derivative with respect to y is 0. So, this is what is my dou m by dou y. I will check what is dou n by dou x. That is here also first term 6x square y, second term with respect to x again 6xy square, third term function of y, x derivative is 0. So, clearly both are same. So, this condition is satisfied. So, this implies the solution, the general solution of the equation. The general solution of an exact equation, exact ODE, is, we have seen this, x naught to x m of, you are doing with respect to x. Okay, so, x keeping y as it is as a variable, plus you integrate y naught, which is fixed number in the domain of the differential equation, to y, which is a variable. You integrate n of y dy, x you are fixing, this is going to be x naught equal to constant. So, this is the general solution. So, let us see what exactly this is. So, we will fix, let where c is arbitrary constant. So, I can directly write the solution. This implies What is the solution? M dx, this is m, whose x derivative is simply x power 5 plus 3y square, so that is going to be 3x square is x cube y square minus x square y cube that I integrated with respect to x by taking x not equal to 0. If I take x not equal to 0, this is what is the result. You can also take y not equal to 0. If you take x not equal to 0, in n you are fixing x naught which is equal to 0, this becomes only minus 5y power 4 that you are integrating with respect to y. Okay, so that will give me minus y power 5 equal to constant. So this is the general solution of the given differential equation. Okay, this is the given differential equation whose general solution is given by this, where c is an arbitrary constant. Now we will consider differential equations of first order, ordinary differential equation of first order, which are not exact but can be made exact. So how do we make them exact? So given equation, so let us say we have a given differential equation, given ODE, first order ODE as m dx plus n dy equal to 0. M and n are functions of x and y. Is not exact. Okay, that means the condition is not satisfied. It's known that it is, let us say it is known that you verified, okay, that dou m by dou y is not exactly equal to dou n by dou x. Such an equation you have got. So what, how to make this equation an exact equation? Is a concept called you multiply some function to the equation m of xy dx plus n of xy dy equal to 0. For this equation, left hand side you multiply some function mu of xy. So left hand side I multiplied, right hand side is 0, so it is 0. So if I multiply like this, of course mu of xy is non-zero, where mu of xy is non-zero. If I multiply this, what function I can multiply so that this equation becomes an exact equation? So that means now the equation becomes mu m dx plus mu n dy equal to 0. So now my m n r, this is my m, this is my n. If I multiply some function of xy which is mu, so that this equation is an exact. So what is the condition of exactness? Condition for exactness now becomes dou y of m. M is now mu m, okay, should be equal to dou x of mu n. So that means mu y I write like this. This is a subscript, denotes the partial derivative. Mu is a function of xy, so subscript y subscript means partial derivative of mu of xy with respect to y. Okay, m plus mu times m y, partial derivative of m with respect to y, equal to mu x n plus mu times nx. So this implies n mu x, I am just arranging it, minus m mu y equal to mu of mu times nx my minus nx. Okay. So, if mu is a function of xy, that should satisfy this equation. Okay. So, that should satisfy this equation. So, if I can multiply some function mu of xy, so that if this satisfies this equation, I can hope to make the equation, given equation, exact, okay, by multiplying this function mu. How do I do that? So, how do I find such a mu? So, what I do is, you consider, so we have my minus nx divided by n mu x minus m mu y equal to 1 by mu. Okay. If mu is a function of x, for example, if you are looking for some function mu that is only function of x, then mu y is 0. Okay. So, this is what the above equation becomes. Mu has to satisfy, which is function of x y. Suppose sometimes instead of multiplying mu of x y function of two variables, if you multiply only function of one variable, let us say mu x, let mu of x y is only function of x, then if it becomes exact, then what happens to this equation? This becomes my minus nx dou m by dou y minus dou n by dou x divided by, this becomes n mu x equal to 1 by mu, because mu y is 0, because mu is function of x only. Okay. So, this implies my minus nx divided by n equal to, what is mu x? If it's mu is the only function of x alone, dou mu by dou x is nothing but d mu by dx into 1 by mu. If I take this mu x this side, that is actually d mu by dx. Okay. So, this implies, now I can arrange it in such a way, d mu by mu, this one I write, which is equal to my minus nx by n into dx. If mu is a function of x, which I multiplied to the equation, then if the equation becomes exact, then my mu should satisfy this. Okay. My mu should satisfy this differential equation. If I want to solve such a mu, this function mu dou m by dou y minus dou n by dou x divided by n should be function of x. Okay. Then only I can get such a mu. Okay. So, what should I check in this case? So the check is, what we should check is dou m by dou y minus dou n by dou x, this you see that which is not 0, divided by n. If this is whether this is function of x only, if this is the case, then I can do it. Then I can integrate this. How do I integrate this? D mu by mu equal to, let us say, function of x, which you call it some phi of x, function of x. So, this becomes phi x dx. So, this is simply separation of variables. This implies if I integrate both sides, this is what it becomes, right. So, I can integrate, c is the integration constant, that will give me log mu equal to integral phi x dx. Because phi we do not know exactly what it is, so we do not know. So, this gives me what exactly my form of mu. Mu equal to exponential of integral phi x dx plus e power c. So, into e power c. If c is an arbitrary constant, e power c is also an arbitrary constant. So, I say some arbitrary constant c1, where c1 is e power c. So, I multiply such a function e power integral phi x dx, where phi x is this, which I check whether this function is function of x alone. In such a case, I can get my function mu as function of alone, only function of x alone. So, now I got what my mu as a function of x. If I multiply this, I can make the equation exact, so that I know how to solve an exact equation. I know how to solve an exact equation, so I follow the procedure to get the solution of a non-exact equation, which I made it exact by multiplying mu. How do I know my mu? I check this condition, so that it is only function of x. If it is only function of x, then I solve this equation, I get this form. Okay. So, now let us see other situation where such a mu, suppose we look for mu as a function of y alone. This is case 1, this is case 2. Okay. So, you can think of this as case 1 and you have the case 2. So, we can get many cases like this. General case I will discuss. First, we will see when then in case 2 we will see mu of x y is only function of y. If I look for such a function of y, what happens to your equation? So, this is the original equation. So, this becomes this becomes what? My, then we get my minus nx divided by n mu x, because mu is function of y alone, n mu x will be 0, divided by, so what we get, denominator is only minus m mu y, minus m mu y equal to 1 by mu. So, this implies you get mu is function of y, mu y is the dou m by dou y, which is nothing but d mu by dy into 1 by mu equal to dou m by dou y minus dou n by dou x divided by minus m. So, this I can integrate if I write like this. If I separate the variables, d mu by mu equal to my minus nx divided by minus m into dy. So, when can I solve this, when can I integrate this equation? If this function is only function of y, then I can integrate both sides. Okay. So, what is the check now? So, we will check whether this function is dou m by dou y minus dou n by dou x divided by minus m is function of y alone. Okay. A function of y only. So, given differential equation, which you know m and n are known, so you calculate this. If it is only function of y, then you solve this. So, by integrating this equation, integration will give me log mu, which is equal to integral phi y dy plus c, which is an arbitrary constant. That implies you get mu as e power integral phi y dy into e power c, that you can say an arbitrary constant. C1 is also an arbitrary. But I need only function. If I multiply this, I make the equation exact. If I multiply with some constant is also fine. If I choose mu as e power integral phi y dy, if I multiply this to your equation, that it can also be made exact. I can choose any value for C1. So without loss of general, you can choose C1 as 1. Okay. So this way you can get integrating factor. So this is what is called integrating factor. This is called integrating factor method. So what I do is I make the equation, given equation, you know that in a priori you know that the given equation is not an exact equation because this condition is not satisfied. So you multiplied mu, which is called an integrating factor, so this is called mu is called an integrating factor. So if I know that if I multiply the equation mu of xy, this becomes this in general, then I hope that the equation becomes exact for such a mu, then that means it has to satisfy this condition of exactness that actually equal to this differential equation for mu, which is function. Actually this is a differential equation, it's not a ordinary differential equation because mu is a function of xy, you have a partial derivatives, this is a partial differential equation actually. Okay. So mu is an unknown, mu is a dependent variable which is, and x, y are independent variable, capital M, capital N are known. So this is actually PDE. You can see actually PDE here. So you don't know how to solve this because it's partial differential equation. Because you have two linearly independent variables x and y. If I view this as a differential equation. So you have two cases. When you look for mu as a function of x alone, if you want, this has to be function of x alone. So that means you have to check, you can check this condition, then you can find such a mu. So you can take C1 as 1, that gives you e power integral phi x, which is this, as your integrating factor. Similarly, if you look for if you want only function of y, if you check that this condition, if you verify that this is function of y alone, then you can find your mu an integrating factor as function of y alone. So we will do some examples in these two cases before we go for general case. Okay. So example, let's consider, try to solve the ODE x square y plus y plus 1 dx plus x into 1 plus x square dy equal to 0. This is what we want to solve, and you can see clearly m is this x square y plus 1, n is x into 1 plus x square. You can see the condition that you can verify that dou m by dou y, that is x square, which is equal to dou m by dou y, dou n by dou x, which is equal to 1 plus 3x square. This is not same. So the equation is not an exact. We cannot apply our method for exact equation to solve the exact equation. So what we do, we know dou m by dou y, dou n by dou x. So you can see, you can verify either my. So dou m by dou y minus dou n by dou x is equal to, not is equal to, this divided by either m or n. If I divide with n, it should be function of x alone. I will verify this. Okay, verify this one, which is equal to x square minus, so 1 minus, what do you get? So dou m by dou y minus dou n by dou x sorry, this is not x square, so this should be x square plus 1 dou m by dou y, okay, so which is not same. So you calculate dou m by dou y minus dou n by dou x, so you have minus 2x square divided by n. What is n? X into 1 plus x square. So clearly I have 2x divided by 1 plus x square is function of x alone. So my integrating factor I have already calculated is mu is e power integral whatever I get here, this is my phi of x, that is minus 2x divided by 1 plus x square dx. Of course with constant that I can take it as 1. So this is equal to, what is the integration of this? E power minus log 1 plus x square, because for any x positive or negative, 1 plus x square is always positive, for which log is defined. So this is exactly our log of this is actually antiderivative of your 2x by 1 plus x square. So this is the integration, this is equal to 1 by 1 plus x square. So this is your integrating factor. So if I multiply this to the given equation, so this implies integrating factor is known, so you multiply this to your equation. So 1 by 1 plus x square into m, that is x square y plus 1 dx plus x into 1 plus x square divided by, so I multiply this second term, so that goes dy equal to 0. Now this equation is an exact with this m with this n, okay, you can verify that. So you can easily say that now dou, this is my m, this is my n, dou m by dou a y equal to dou n by dou x, which is 1, okay, so verified. Now the solution, the general solution, that implies the general solution is what you have to do, integrate from x naught y naught, x naught to x, which x naught I always take it as 0 because 0 is also part of the domain. So here x is full real numbers, so I can choose x naught as 0. Y also there is no issue, so y is also can be full real numbers. Y naught also I can take it as 0. 0 to x square plus 1, so that is going to be y. These two terms if I do divide it, this will have y plus 1 by 1 plus x square dx, okay, plus y naught is 0, if I can choose my 0, y naught is 0 into y x naught, that is x naught, if I put x by x naught which is 0, so it's 0, so 0 dy equal to constant. This is my solution, this is anyway 0, so this implies what is the solution? You can see xy, if you integrate the first term, that is going to be xy plus tan inverse x, tan inverse 0 is 0, minus tan inverse 0, that is 0, okay, equal to, this is 0, so constant. So this is your general solution of the given non-exact equation, which we made as an exact equation like this, and then we solved with the procedure that we know already, okay. So in this so far we have solved some exact equations, and we explained the method how to reduce certain non-exact equation into an exact equation, and then we can so that we can integrate the equation to get the general solution of the given differential equation, first order ordinary differential equation. This is the method called integrating factor method. So we have seen we have seen the integrating factors that are only functions of x or y. Okay, so we have explained the method, what to check, what expression to check to make the given non-exact equation into an exact equation, so that the integrating factor will be only function of x or function of y only. So, we will see the general method in the next video.